Welcome to our Group 39 presentation on the safeguarding of biodiversity in the flow countries. The flow country is a unique and critical ecosystem located in the northernmost part of Scotland. The flow country's peatlands, often referred to as one of Europe's most extensive and significant peat bogs, play an essential role in climate regulations and carbon sequestration. However, recent new reports have highlighted several phenomena of biodiversity decline and their underlying cause. First, decline of aquatic plants and species, such as savanna moss. This issue is directly caused by the lowering of the water table in the peatlands. As mentioned earlier, peatlands have a crucial carbon store because healthy peatlands have a thick layer of savanna moss that can actively secrete more carbon. Lowering the water level affects microbial activities, such as the methane-producing bacteria, which in an aerobic environment rapidly convert organic matter in the peats to carbon dioxide. This significantly reduces the carbon storage capability of the peatlands and lead to their degradations. Second, decline of native bird species and introductions of invasive foreign birds. This is primarily due to current afforestation activities, which has led to the loss of native bird habitats and specific isolations. In this presentation, we will propose 4 engineering solutions from 2 different perspectives: strategies implementations and monitoring management to address these issues. Here comes our option 1, improve flow countries' hydrology.
Why adopt an electrical power system? We had 4 answers for this question. First one is vast area. The second one is geographical features. Third one is abundant marinage. Finally, exceeding wind power projects. Next, I will introduce how to address the hydrological system. There are 5 ways to do that. The first one is power generation. It has tidal energy, wind energy, and solar energy. Second one is power transmission. 3 parts for that: high voltage, microgrid, and energy storage system. Third one is smart control system to neurogrid system, and finally, peatlands. So now let's conduct a SWOT analysis regarding the strengths of this plan. Firstly, the solution could address the energy problem. Secondly, the water table of the peatland will no longer be dependent on climate conditions. Next is about weakness. Firstly, it requires a significant investment in infrastructure, and then peatlands have complex terrain indeed. As for opportunities, firstly, government policy support is really important, and then growing awareness of peatland conservation is crucial too. Finally, regarding threats, there has environmental impact and the economic return risks. So this is our hydrological plan for improving flow country. Thank you.
Now let's move into the option 2, the smart water management.
My engineering method is smart water management. It divides into 3 parts. The first part is setting sensors and digitalize peatland soil data. First is setting up water level monitor sensors, soil moisture sensors, and water quality sensors. Second is monitoring the health of peatland and the changes in vegetation using UVA and EO technology in real time. The second part is automated irrigation system. First is to create an AI-driven precision irrigation system. Second is establish of AI control mini drains to prevent damage from high water levels. The third part is the feedback control. It divides into 3 main parts. The first part is sensors. The second is AI control system, and the third part is automated irrigation systems. And according to the SW analysis of my methods, they divide into 4 parts. First is strength, precision management of enhanced conservation efficiency. Second is minimizing human disturbance and reducing ecological risk called P-based fronts. Third is smart monitoring enable rapid detection of environmental anomalies, allowing timely restoration actions to mitigate long-term ecological impacts. The second part is weakness. Long-term data accumulation analysis are required, and the high complexity and the dependence on expertise. Third is peatlands hydrology and biodiversity are influenced by climate change, precipitation patterns, and invasion species, requiring continuous optimization of a precision agriculture system. And the opportunity of my method is the UK Environment Act supports peatland restoration. And the threat of my method is uncertainty of climate change. Thank you.
Next, let's see the option 3, ecological corridors.
Okay, for ecological corridors. Due to social and economic developments, large-scale afforestation has significantly altered peatland, driven by government tax incentives. Over 800,000 hectares of open peatlands in the UK have been converted into commercial plantations. In North Scotland, particularly in Caithness and Sutherland, approximately 6,700,000 hectares of peatland have been afforested, and the infrastructure of this project will be constructed in Flow Country, the largest peatland in this region. And the ecological consequences. Afforestation has had several ecological impacts on native species, especially birds and other peatland-dependent wildlife. Habitat loss. Forest plantations replace native peatland ecosystems, reducing suitable breeding and feeding grounds for birds. As an effect, the fragmentation of open peatland creates isolated habitat patches, restricting species movement and limiting gene flow, which increases the risk of local extinctions. Our proposal is that build ecological corridors to mitigate the fragmentation caused by afforestation. We propose the construction of ecological corridors within afforested areas. These corridors will reconnect isolated peatland habitats, allowing birds and other species to migrate safely. By implying this strategy, we aim to restore ecological connectivity, enhance species interaction, and protect the integrity of peatland ecosystems. Next, we will introduce the open peatland corridor. The open peatland corridor is designed to support peatland birds as well as some mammals. It features low vegetation cover. Structurally, it mimics a natural open peatland landscape, ensuring minimal obstruction for species that rely on open spaces. One key advantage of this corridor is that it reduces forest effects, meaning it is less likely to attract woodland bird species. Additionally, its wider width, typically between 400 and 500 meters, ensures that birds can move safely without being affected by other species. This corridor is particularly suitable for connecting large fragmented peatland areas, helping species that have been isolated due to afforestation. We also have a SWOT analysis for this plan. It has many strengths. I think the key strength is that it has policy support and potential funding. And it also has enhanced ecological connectivities. I think it is a good plan.
Finally, let us see the option 4, ecological monitoring and restoration assessment system. Earlier, my teammate proposed 3 practical strategies. However, observing improvement during implementations requires a long biological cycle. To reduce trial and errors costs, real-time monitoring and adjustment of the strategies could make a significant difference. I will introduce a data fusion model that combines remote sensing and ground monitoring data to predict gas emissions and assess the effectiveness of restoration measures, providing scientific support for optimizing restoration strategies. The models consist of 3 key components. First, data source. Here I only showcase the data acquired from Freeze observation platform based on satellite remote sensing technology. Second, model constructions. Using machine learning and statistical methods, I developed two models. First is the gas emissions prediction models. Another one is the restoration effects evaluation models. The logic of this model follows the structure below. Finally, model validation and optimization. This part involves comparing model predictions with actual monitoring data to validate accuracies and reliabilities, adjusting models parameters based on comparison errors. The model has three main applications. First, restoration measure evaluation, helping guide the selection of the most effective strategy through pre-measurement evaluation. Second, dynamic monitoring and adjustment. The model can be updated with real-time data to optimize peatland restoration strategies. Third, long-term climate adaptation plan. Based on this scientific analysis, the model provides support for future adaptation efforts. I also conduct a SWOT analysis of this engineering solutions. Due to the time, I will just highlight some key points. There are two main strengths. One is that it has low cost because it relies entirely on existing equipment and data source, avoiding the need for the new infrastructures. Another one is it enables the real-time monitoring and restoration assessment, which allows for quick detection and resolution of environmental issues, minimizing the negative impact. Well, a key weakness is that the model is based on the pre-recorded data, so it cannot predict unforeseen extreme weather events or human interference. This is the introduction to the engineering solution based on the mathematical modeling. Based on the SWOT analysis conducted earlier, we have identified three key criteria for decision-making. First, implementation cost. Second, environmental impact. Third, technical complexity. In the table below, we can see that option 3 have the lowest implementation cost, the least human interventions on the environment, and the lowest technical complexity, all of which are marked in green. Therefore, we have selected option 3 as a preferred choice. To address the limitation of option 3, the long implementation cycle and difficulties in observing the improvements, we have combined option 3 with option 4, which allows for real-time monitoring and comparisons of simulated improvement with actual change. This combination of option 3 and option 4 forms our final optimized solutions. Finally, we have a dedicated slide listing the reference we use for the project. This is all our presentation. Thank you for listening.